looks like I'm blurry. We can't have that. That looks terrible. There we go. Not much better, but at least you know what you're looking at now. Okay. All right. Okay, good morning, everybody. Monday morning. Let's get started with stuff. Okay, we had a couple more people take the survey, which is good. We're getting close, right? I have hopes that I can release the sample material, your survey results on Wednesday. That would be great if I could get that released, and then we will. Then you can start digging into all that stuff. Dive right in and start getting all that kind of stuff done. Ask me questions, whatever you need, so that you can move forward with that. Let's see. Do we have one that's about to be due? No, that's right. So that's right. I have my 2 stats class, so I have to remember which one I'm in. So all these dates are going to be updated. You can't see them yet because they're not released. But once we have that survey stuff released, I'll go through and I'll change all these dates so that you have a little bit of time to work on each of the, a week or whatever is reasonable to get these done. So hopefully Wednesday I can release the data. I'll start releasing these with due dates that are updated based on when that data is released. And then you can come to me and go, oh, let's see, I got 5 days to get this done. I don't quite understand it. You'll get together in your groups, that kind of stuff. So we'll talk a bunch about that on hopefully Wednesday, right? I hope if we can get a few more people. By the looks of it, you're still going to be well short of what you would want because I don't think we're going to get another, let's see, 16 people. If it was this hard to get to 20, we're not going to get another 16 people by Wednesday, but it would be good if we could even get a few more people, right? At this point, the sample size is so small in this class 20 that even getting, a couple more people, two more people would be a 10% increase, right? So even a few more people is just going to make it that much easier. At this point, sort of every person counts taking that survey. So hopefully I can update you on that Wednesday and sort of show you how things work. We're kind of getting near that end of October, right? It sort of seems like we were just in the middle of October, and yeah, we're just a couple days past the middle, but this week is one of those weeks where it's going to start to seem like all of a sudden, time's starting to fly because we're a little bit past the middle of the semester, and at that point, each week that goes by, you're sort of hurtling towards the end of the semester, and things start getting busy because you got a project to work on in here, you got essays to write in your English class, and you got other stuff going on in your other classes besides work, and so some of you, your jobs will be affected by holidays and different stuff. So it's going to start getting busy. So today we are going to finish. We're going to kind of talk about this 3-5 stuff here. Actually, really interesting stuff. I find it actually interesting to talk about some of that stuff that's in here. You can do some really interesting type problems. So we'll finish out this chapter 3 stuff. It says you've got till October 24th, but remember that you kind of have 3 chapters all due pretty near each other. So hopefully you're not looking at that and going, oh, I got time, because you want to remember, oh yeah, this one's actually due like the next day, this other chapter, and then, oh yeah, this one's due the day after. I'm probably going to take this probability chapter and change those due dates a little bit. I'm going to push them out to give you a few extra days. That doesn't mean a lot of days, because, we're kind of bumping up against the next chapter then that's due after that, because we got to get through these chapters by the end of the semester. But I'll push this last one, chapter 5, out a little bit so you have a couple extra days, but that's just chapter 5. Okay, make sure that you're getting chapter 3 completed, and then make sure that you're hopefully starting to work on chapter 4. I should be able to talk about chapter 4 next time. I think I can talk about everything we want to talk about next time on chapter 4, and then you should be able to get through that. Now, you should be able to do it anyways. It's not like you have to wait for me to talk about it in class, because you have the lessons right here, and they just sort of walk you through how to do it. So, don't like wait for me to get the work done. Go ahead. If you're ready to be, some of you probably have finished chapter 3. If you're ready to start in chapter 4, go for it, right? Get that done before that due date so you're not stressed out and right before it's due. Okay, so that's what our plan is for this week. I hope everything goes well. Hopefully Wednesday I can release the data stuff for your data, update the project assignments to reasonable due dates. Then all these assignments are going to be due. That's kind of, or well, I guess you still have time. You have almost a week for 3 and 4, but like I say, don't wait on those. They're not terribly difficult chapters if you know if you're like, you watch the videos and you know what's going on. They're not super difficult, but they do take some time to work through, and there are some things that can be confusing for students. So don't wait till the night of the due date and then think, oh, I'm just going to blast through everything, because then sometimes you get to a problem you don't know how to do, and you don't understand something about it, and then you're stuck on that. One thing to look out for, remember, there's a difference between standard deviation for a population and standard deviation for a sample. Those are not the same thing. That's kind of the number one thing that I see, like in chapters 3, and I think chapter 3, a number of different problems come up where they say treat this as a population, whereas we're kind of used to treating things as a sample, because that's what you usually do in statistics. So if it says treat this as a population, make sure you're using that unadjusted standard deviation for your calculations and not the standard deviation, right? Make sure you're doing that if it says treat this as a population. Otherwise, you use what says standard deviation, right? So that's kind of the thing I've seen the most between my 2 stats classes confusing people is that. So you just have to read closely and ask yourself, because the mean is the same either way, right? Your calculation doesn't really change. You just take all the values, divide by the number of values. But your standard deviation does change if you're talking about a sample or you're talking about an entire population. So, and StatCrunch will give you both. You just have to make sure you pick it in that when you do that summary, when you go into the, in fact, let's look at it just so we can make sure everyone understands. So I've got 2 columns here. That's for an example we're doing today. So you go into your summary stats. Oops. Where are we? Summary stats columns. Right, and it's already grayed out where it gives you your standard deviation. That's always in there. But that's if you're using a sample. If it says population, you got to come down here and pick this unadjusted standard deviation. You got to pick that one and include that one. And that's what you should be using in your calculations. And I know I don't remember exactly which problems I assigned for this one, but there are times where the stuff we're covering today will say treat this as a population. And it certainly has in the few sections that we've already talked about, right? So hopefully you're comfortable with that already. But I know there's a few students always who kind of miss that point, and then they really they're doing the right thing, except they're using the standard deviation instead of the unadjusted standard deviation, and they just get stuck and can't really figure out why they can't move forward. So make sure you're paying attention to that, okay? Okay, with that said, I think that's everything I want to talk about. So let's go ahead and dive into things a little bit. So here we have measures. So let me see. I can do better than this. What if we do this? And I had to resize everything because I was in a meeting the other day. Let's see. That looks pretty good. Is that going to work on StatCrunch? There we go. Look at that. Everything's lining up just fantastic. Okay. Okay, so measures of relative standing and box plots. And box plot is really a way, it's a visualization that can seem kind of weird, and at first you can kind of look at it and go, okay, I've memorized what I'm supposed to do, but I don't really get it. Once you kind of understand what the box plot is, you'll realize it's showing you some measures of relative standing in a visual way, which actually can be super convenient sometimes. Can really tell you some stuff about the shape of your data in a way that the other visualizations we've looked at can't do. They kind of come up short, okay? And here we're going to look at z-scores. I actually think z-scores are super cool. You can do some really interesting problems with z-scores that would be really hard to answer any other way. And if you look the equation for finding a z-score is like super easy, right? It really couldn't get much easier than this for a z-score. You just, I haven't explained it yet, so of course you're looking at it and going, well, I don't really know what it means. Yeah, we're going to talk about it in a minute, but as you can see, there's not a whole lot going on, right? It doesn't look like the quadratic formula or something like that, right? It's just there's a subtraction and a division. That's it, once you have your numbers. So, this section introduces measures of relative standing, which are numbers showing the location of data values relative to other data values within the same data set. The most important concept is the z-score, which we will use again and again. Sometimes you use z-scores and you don't know it. It's kind of like the standard deviation and sometimes the mean. We'll do stuff later in the semester where you feel like you're doing something that is not calculating the mean or the standard deviation because you go in and you do a hypothesis test or whatever. But inside of that calculation in StatCrunch, there's a mean and a standard deviation, and sometimes z-score is being calculated. So even though you don't realize they're being calculated, they're in there, right? So it's an important part of understanding the concept. And that's why sometimes, like you'll hear me say it, and when we're in class, I have a few exercises we do. So that even though you have a formula and StatCrunch is going to do it for you, it's good to work through it a couple times because then you go, oh, I see the mean is actually inside of this other thing that we're calculating. They come up in there. So let's take a look here. So z-scores. So a z-score is found by converting a value to a standardized scale. What does that mean? We'll talk about that in just a second. As given by the definition down here. So with this z-score, let me move this. I can make this a little bigger, huh? Maybe, and move it over like that. So a z-score or standardized value, you almost always are going to hear people say z-scores when they're just talking about it. But sometimes you might hear someone call this a standardized value. Is the number of standard deviations that a given value x is above or below the mean. The z-score is calculated by using one of the following. So again, it's back to sample versus population. But if you look, the denominator is the standard deviation, right? So remember, here's where you have to pay attention in the homework problems that you're doing. Does the homework problem that you're doing want you to treat your data as a sample? Then you use this one over here. Does it want you to treat it as a population? Then you use this one over here. And if you're sort of not familiar yet with the symbols, you go, well, what's the difference? It kind of seems like the same thing. Well, remember, this is your sample standard deviation. That's the one that just shows up as standard deviation in StatCrunch. This one over here is your population standard deviation. That's what StatCrunch calls the unadjusted standard deviation. So again, you have to read your problem to figure out, are you calculating this value down here, or are you calculating this value down here? Okay, so you can figure it out from there. Okay, and then x bar and mu are just x bar is the mean of your sample, mu is the mean of your population, but you almost never know those two things, so that's why it doesn't come up as much. So what does this really mean? What is this? We take a data value and we subtract the mean from it. That's what's going on in the numerator. I have some data value. I'm going to subtract the mean, and then I'm going to divide by the standard deviation. Now, how does that make sense? Well, the first thing we want to recognize about z-scores is that this is a data entry level measurement. In other words, each data value in your set has a different z-score. Okay, so we talked about this earlier in the semester, where there are sometimes things we calculate for each data value in your set, and there are some things that are calculated on the set as a whole. So for instance, the mean is the mean is not different for each data value in your set. There is one data value for your whole set. There is one standard deviation for your whole set. However, with a z-score, each data value is different. Well, it can be different for each piece of data that is in your sample. So if you have a sample with 20 pieces of data in it, you can have 20 different z-scores. Now, some of them might be the same because they might, you might get the same answer twice. There might be two people that are 24 years old. Well, then their z-score is going to be the same. But you see what I'm saying, right? This is one place where I see students get confused about when about these different measurements we have, where is the measurement the set as a whole, or is the measurement really different for each piece in the set? And the z-score is different for each value that's in your sample. okay, or population. But again, all you do is change the standard deviation for that one to the other one. So what this is really doing, this is measuring the distance between your data value and the mean. So if you have an outlier, then the difference between the mean and the standard deviation will be a bunch, right? You'll have a big distance because that mean should be somewhere that you could argue is in the middle of your data, and then your outlier should be really far away. And then you divide by the number of standard deviations. Well, if you take the distance and you divide by the number of standard deviations, what you're actually calculating is how many standard deviations that data value is away. So the same way that let's say you had a ruler, right? Just like a 1 foot long, 12-inch ruler, right? That some people use in different, if you take a geometry class or something, you probably have it around. You take a ruler, you could go up to a wall at the rule you're in, and you could just put that ruler, like keep placing it end to end, and you could measure the length of the wall, right? You could go, okay, I was able to put this ruler down 14 times or 14 and a half times or whatever, so my wall is 14 and a half feet long, right? Well, essentially, that's what we're doing here, but not in a physical sense where we're measuring like a physical wall and measuring the length of it. We are measuring, but really kind of the same idea. You're figuring out how far your data value is from the mean, and then you're putting the standard deviation down end to end to figure out, well, how many standard deviations is that? So this is telling you how many standard deviations that data value is away from the mean. So if you have a value that's in close to the mean, which is where you would expect a lot of your points to be, and a lot of the time, you expect a lot of your data values to be near the mean. We've seen cases where that's not true, but if you have like a normal curve or something like that, you're going to see a lot of data values around the mean. Those z-scores are going to be very small. As you go out to the edges of the bell, you're going to see larger z-scores because that distance is further away. Let me see if I can find a graph here. So in other words, something like this. Oops, it's not up high enough. Here's our mean in the middle. The z-score is really showing us how many standard deviations away. So like right here, this line, that's a z-score of 1 because it's the mean plus 1 standard deviation. So this is 1 z-score. So any data right here would have a z-score of 1. Here you'd have a z-score of 2 because you're 2 standard deviations away from the mean. And here you'd have a standard deviation of 3 because you're 3 standard deviations away from the mean. So you might have a less than that. You might have a value right here might be like 0.27 for the z-score because it's 0.27 standard deviations away from the mean. Right? If you exactly match the mean, your z-score would be 0 because the distance between the z-score and the data value would be 0. Okay? And you can be below the mean as well. When you do that subtraction, you might get a negative number. So here, this would be a z-score of -1. This means you're 1 z-score or 1 standard deviation away, but in the negative direction. Here, this would be -2 for a z-score. You're -2, right? This one right here might be -2.5. -2.5 standard deviation, so you're moving to the left, to the negative side of things. Here would be -3 and so on. So that's really what we're looking at when we're talking about these z-scores, right? So it's easy to just sort of go, oh, the z-score is 0.7 and kind of forget what it means, but then you just want to stop and think to yourself, oh, this means that my data value is 0.7 standard deviations above the mean. And especially as you sort of start to remember this graph more and more, this can come in handy because you can kind of remember, oh, that means this much of my data should be below this value. There's all sorts of things you can bring in if you're understanding these tools, okay? But you kind of have to make sense of them first. So this is actually a really good graph to look at when you're trying to make sense of standard deviations because it's showing you, yep, here's my standard deviation ruler. I put it down, it takes me to this point. That's 1 standard deviation. That's the z-score of 1. Then I pick my standard deviation ruler up, I put it down here, and it takes me to here. Just like I was talking about, you'd put a ruler along the wall and see how long the wall is. We're putting our standard deviations down here and seeing how far particular data values are away. We can also use this to figure out if something is technically an outlier or not. Like under certain conditions, you may want to say, we're going to consider outliers that have a z-score of this or more. Well, if you do that, then it's very clear what's an outlier and what isn't, right? You don't have to sit here and wonder, like, is this thing an outlier? You've said, no, for our purposes, we're going to call an outlier anything that's 3 standard deviations above the mean or whatever. So then, okay, well, if your z-score is above 3, then that's an outlier, and then you can deal with it however you please. Okay, making sense so far? So let's just do a problem here so you can kind of see how this goes. So here's example 1. Oh, right. So this was the problem that we did. Actually, this isn't the one I want to do, is it? Well, let's just look at this one. So if you've got the regular chocolate Chips Ahoy cookie, 30 chocolate chips there was 40 cookies that were sampled, I think. They had a mean of 24 chocolate chips and a standard deviation of 2.6. So if you want to take, you randomly select a cookie from the container. It's got 30 chocolate chips in it, right? The mean was 24. And the standard deviation you calculated was 2.6, then you're just plugging the stuff in here. 30, that's the one for the particular data value that you are interested in, is this one. 24 chocolate chips, that's the mean. So we're figuring out the distance between 30 chocolate chips and 24 chocolate chips. That's 6 chocolate chips. That's the difference between these two data values. And we divide by 2.6 chocolate chips, which is the standard deviation. That gives us 2.31. So a z-score of 2.31. So you can see, really not a difficult calculation. Once you have the mean and standard deviation, there's a subtraction and a division. As long as you do those in the right order, you should be good to go. And then you can get your z-score. Now, you're going to have problems on the homework where they want you to calculate the z-score for each individual data set or data item. And it just doesn't take very long. Once you have the information, it's like it may take you a minute or two to calculate those. You can do them by hand. Those of you who want to get fancier, there's a way you can do, it's not exactly scripting, but you can kind of think of it like those of you who have, excuse me, those of you who have ever used Excel or Google Sheets or something like that, and you put a formula in there so that you have a column of data, and then you can create another one where you have it do a bunch of calculations for you. You can do that in StatCrunch and have it calculate the z-score for your whole column at once if you want. I'm not going to spend time on that because I'm trying to make sure everyone gets the basics so that they understand what's going on. If you feel really comfortable and you're like, oh yeah, I've used Excel, I'm totally comfortable with Excel or Google Sheets and equations in there and formulas and stuff like that, feel free to look up a video on it. Literally, if you just look up, like I've kind of recommended, whenever you're stuck, just look up StatCrunch and the thing you're looking for. So go on YouTube and look up StatCrunch z-scores. Someone's got it set up where they're going to show you how to do that. So if you are comfortable with putting formulas into spreadsheets, then by all means, go watch a video, and then you'll learn it'll be a little bit easier for you. Those of you who get confused with formulas and you're not familiar with putting formulas into spreadsheets, don't worry about it. You're just going to calculate these by hand, and you're going to have to do it maybe like 7 times for the particular problem, which isn't that bad because remember, it's just a subtraction and a division. So you should be able to do the whole thing in like a minute. But those of you who are comfortable with those kind of spreadsheets, you'll go in, you go to StatCrunch, you'll go into, so the first, here's what step 1 would be when you get to that problem that says calculate all the z-scores. You'll come down here, get your summary stats, pick columns, you'll pick the one that you want, and then from the problem you're working on, you have to ask yourself, am I treating this as a sample or a population? If it's sample, you're good, just leave the standard deviation here. If they say a population, you need to come down here and grab the unadjusted standard deviation and use that one. So you have to read closely. But then it gives it to us. You've now got your mean and you've got your standard deviation right here. So now you can start doing the calculations, for the 7 problems that you have. It's easy. It's just the data value minus the mean divided by the standard deviation. Do that 7 times and you'll get it. For those of you who want to get a little bit fancier, you can go into data. And where is it? I have to double check because I don't usually use it very often. I think it's here. I think you go, it's under data. I think it's under compute. But just watch a video online and you can actually tell it, okay, take this data, take the data value from the column that I'm choosing, and then you would subtract whatever your mean was that you calculated. You subtract that number, put it in parentheses, divided by, put the standard deviation. And if you do it right, if you follow the videos online on YouTube, it'll just create a whole column for you and you'll get all your z-scores that way. I think in most of those problems, there's not more than like 7 points. So doing it by hand is not like difficult. Okay, so if you do it by hand, it's easy. Take you a minute or two, no problem. If you're fancy with spreadsheets, you can have it do the whole column for you at once. It doesn't really matter which one you do. Either way, you're going to be done in a minute or so with the problem. Where am I? Okay, so you can do those z-scores. So this is one of those things that's kind of different depending on what book you look in. There's some of the rules of thumbs for statistics vary a little bit depending on the book that you're using. We usually consider something that's more than 2 standard deviations away to be an unusual value. So all that means is if you have something that's z-score is 2 or higher, or you have something where the z-score is -2 or less, just look at those values and ask yourself, is something going on here? It may be that it's worth taking a look at those values. It may be that it's not. It depends. Certainly, if your z-score is getting up to be around 3 or higher, definitely look at those points and ask yourself, is something different about this? What is different about this value? Or if it's -3 or lower, take some time to look at those values and ask yourself, I wonder what's different here. I wonder what's causing this data value to be different than the rest of them. Okay, z-scores actually get used sometimes in medical tests, right? So because it kind of makes sense that you would return things that way. So if you go, we're talking about relative standing here. If you go take a test and you get some cholesterol level, some number comes back and it's like, well, okay, but what does that number mean? If they put it in a z-score, then they can start to figure out where you fall relative to everyone else. Remember we talked about like relative z-scores? So or relative, what is it called? Relative standing? Yeah, measures of relative standing. I'm getting the terms mixed up. So how those things are relative to each other. So you can go, well, I don't know, there's some number here about my cholesterol level, but what does it mean? Oh, well, you're in the top 10% for cholesterol levels in your blood, which is not a good thing. And then, so that's kind of a red flag, like, oh, you probably should be careful. You probably should, maybe they're going to recommend to put you on a statin, or that you change the way you eat or something like that, right? So sometimes medical stuff is given in z-scores. Properties of z-scores. A z-score is the number of standard deviations that a given value x is above or below the mean. It's important that you realize that. We're essentially taking the standard deviation and using that as our ruler to measure the distance between the mean and our data value. Z-scores are expressed as units as numbers with no units of measurement. That's because they cancel out, right? When you do the calculation, since the standard deviation has the same units as the mean, when you calculate it, your units just cancel out entirely. You're basically getting but you can think of it as it's this many standard deviations from the mean. You can sort of fill it in with a sentence, right? We consider a data value a little more extreme if it's bigger than +2 or less than -2. Right, and then any value above your mean should have a positive z-score. Any value below the mean should have a negative z-score. Okay, so we can kind of go through those. And in fact, I think for time, we may not have time to do the example I was going to do, but I think you'll get z-score. People seem to be getting z-scores when they do the problems. Okay, percentiles. What is a percentile when we talk about those? Percentiles are one type of quantiles or fractiles which partition data value into roughly the same number of values in each group. So here's the definition. Percentiles are measures of location, denoted P1, P2, up to P99, which divide a set of data into 100 groups with about 1% of the values in each group. Now, percentiles are not exact, and in fact, if you look in different textbooks, they'll actually tell you to calculate the percentiles slightly different ways. Now, it doesn't really matter because when we're dealing with percents, you're usually kind of doing things from an estimate standpoint anyways, right? Like the example I give, when we surveyed students on campus and asked how many of you support a full tobacco ban, we find in our sample that 82% support a full tobacco ban. It doesn't really matter if the true number for the whole population is 81%, right? It's close enough to give us an understanding of what kind of decisions we should be making, right? So percentiles are inherently a little bit inexact, but they're good enough. They're good enough for the kind of things you talk about. So what the percentile does is it tells you what percent of your data is above or below a certain value. Okay, so for instance, the 50 percentile, that means that 50% of your data is above that, 50% of your data is below that. Do any of you recognize another name for the 50th percentile? If you're current with stuff, the 50th percentile is also the median, right? The median cuts your data in half, 50% above, 50% below. Not the mean, the median. That's also the 50th percentile. So some things are measured this way. SAT scores, I don't know if they're still measured this way, but they used to be measured this way. You would get your SAT score back and you'd go, I don't know, it's like some number. I don't know really what that says. And then it will say, oh, you fell in the, 15th percentile. So it's like, it tells you how much, 15% of the data is above, and what would that be? 85% of the data is below, right? So it's kind of telling you what percent of the group did as well as you or better, right? So that is, again, another measure of standing. Now, there's two ways we can calculate. Well, there's two questions that can be asked about percentiles. One is find the percentile for this data value. The other is find the data value that would have this particular percentile. One's a little bit more complicated than the other, so make sure you kind of look closely when you're doing that. But let's just say you have this, right? You get your SAT score and you want to know what's my percentile of that value. Now, you don't have all the data at home, so you can't calculate this, but this is how the people at the SAT, when they're printing out your thing, this is how it's calculated. Is you take the number of values less than your data value, divide that by the total number of values, and multiply by 100. So what that's basically doing, if you think about it, this is giving you the fraction that represents where you fall in the data. So let's say you get 0.8. That means that, if all the data is laid out in order, you're 80% of the way through that. That's what 0.8 would be as a decimal, would be 80%, right? And then you multiply by 100 to give you 80, and you go, oh, okay, I'm 80% of the data is below the score that I got. Okay, but this is really important. There's an important step here that students miss sometimes. You have to order the data. Sometimes students will take the unordered data and just start counting, but then nothing's going to work right. It's just going to be, you're just all going to get random numbers if you do it. You have to order the data and figure out how many data values are below the data value I'm talking about. So how do you do that? Well, once you have your data in StatCrunch, you can go through, let's see, I think it's under data. You can go through, arrange, and then, wait, is it? Oh, sort. I think it's under sort. So if you have a column and you want to sort it, you pick sort, and it says, do you want to start at the smallest and get bigger, or do you want to start at the biggest and get smaller? So you can choose that your data values are either ascending or descending. Yeah, I might as well do it because we're not going to have time to do this example that I wanted to do. So see how these are unordered right now, this column? So if I go in and do data, sort, I want to take select columns. I want to do, say, the English one. See, it's unordered right now. And I say, I want that to go from highest to lowest. And you can either have it create it in a new column or replace the old one. I'm just going to open it in a new one. Hit compute. Wait, what did it say? Select column. Compute. So you can see now when it goes through, see how they go from greatest to smallest. Otherwise, it's like, don't try to just look at the data, the raw data, and try to figure it out. Like, oh, I'm going to count how many data values are below 83. It's super easy to mess up if you're trying to do it that way. So just do what I did, resort it in another column, and then you can look, oh, here's 83, here's how many columns are below it, right? So it's, you just go into data, sort, and then go from there, okay? If you forget the sorting part, none of it's going to make any sense. It's about to kick me out of there. Let's see. Where am I? Okay. So make sure you do the sort piece. And then, like, for here, what do they do? Okay, list. We've got lists of chocolate chips that were surveyed, and we want to know, find the percentile for a cookie with 23 chocolate chips. So they've ordered all the data, right? See how it's going from smallest to biggest? So you put them all in order, and you go till you hit 23 and go, oh, right here. This is where we hit 23. So that means there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 data values that are less than the data value we care about. So that's where this 10 is coming from. And there's a total of 40 data values. So that's where the 40 is coming from. So basically, where do we hit 23? We hit it 1/4 of the way through our data, right? 10 over 40, 1/4. And then we multiply 1/4 times 100. That gives us 25. That means that 25% of the cookies have fewer chocolate chips than 23. 75% have more, right? And you can see where it gets into a little bit of like, well, why are these inexact? Well, what if you have exactly 23 chips? There's a whole bunch that way. So you kind of can adjust the wording that you use depending on your data set to say, 75% are greater than or equal to the chocolate chips, or however you want to do that. But usually your data sets are so big, you don't really have to worry about that. In this case, it's a small data set, so it makes it a little different. The smaller that data set is, the harder it is to like really say things the right way and really make meaningful results. That's why we want to get everyone taking that survey. Okay, so if you're trying to figure out the percentile for a particular data value, that's the easy one. Look how easy this is. This is a division and a multiplication. All you have to do is sort the data, which I just showed you how to do in StatCrunch, and then you just pick out the right pieces, plug them in here. Well, 100 isn't going to change. That's always there because that's just how you convert to percents. 40 is just the total number of values. So really all you're doing is you're ordering your data like I showed you in StatCrunch and then figuring out this numerator. The rest is pretty straightforward. And again, if you wanted, you could write a little script where it fills in the whole, you could calculate percentiles for the whole column, but you don't need to. Right, and then there's just like this book has you can see it's a little bit more complicated to calculate it the other way. That is, this would be answering the question, what if I want to know the 27th percentile? Like what data value is that 27th percentile? That is slightly more complicated. It's really not bad, and unfortunately, like when you lay it out, it looks more complicated than it is. It's actually not too bad either, but it does take a couple of more steps than the problem we just looked at. So, watch the videos, follow along, take some notes, and then you should be able to do those that one as well. But that's the idea behind what we're looking for when we're talking about percentiles, okay? Okay, then you get into quartiles. What are quartiles? They kind of sound like percentiles, but then quart? What does that mean? Well, remember quart, like quarter, is a fourth. Right? A fourth of $1 is a quarter. That's what we're talking about here. So the first quartile is also known as the 25th percentile. The first quartile has 25% of the data below it. so does the 25th percentile. So the quartile is just a nickname for the 25th percentile. The second quartile, well, let's see. If you have 2 quarters, you have what? You have half a dollar. So this is half. So actually, the second quartile, which you almost never hear anyone say the second quartile, the second quartile is the same thing as the 50th percentile, which is the same thing as the median, right? They all just mean the half your data is above this value, half your data is below this value. Those all mean the same thing. The third quartile, you're probably getting the hang of this pattern here. That's the 75th percentile. So it's the point where 75% of your data, sorry, I'm getting the hiccups trying to start right now. 75% of your data is below this point, 25% is above. And that can be helpful because knowing where this data falls can give you a sense of how your data is shaped, right? Which, you know, we have other ways of looking at that, histograms or whatever we're doing. But this can actually be another really useful way of visualizing your data. Okay, so then they say, like, find the first quartile. Well, that's really just finding the 25th percentile, and then, you know, you follow the directions for how to do that. And then, like, this is what I was talking about. There is not universal agreement on procedures for finding quartiles, and different technologies may yield different quartile values. So it just depends on how you're calculating things. And that might seem like, that's crazy. People calculate it different. The differences that you get are like tiny, tiny little differences. So it's not like one person's going to get that some value is the 37th percentile and someone else gets that it's the 59th. You're not going to get something like that. It's like some person, you know, you might be off by a small decimal, especially if you have a realistic size data set. Okay. We have what's known as the 5-number summary, which is sort of what StatCrunch gives you, but this was back in the day, especially where everyone had to calculate everything by hand. You'd go through and you'd figure out the minimum, first quartile, second quartile, third quartile, maximum. It's nice now. StatCrunch does that. It gives you these, plus it gives you even more. So notice when we go through and calculate my summary stats for, let's say, the math one, and I hit compute, look what we got. We got the min-max, quartile 1, quartile 3. So these things that didn't make sense to you before, look, we're getting them for free. There's your quartiles. And you go, well, where's quartile 2? Remember, that's your median. So you already have that right here. So we're actually easily with StatCrunch, we get better than, we do better than the 5-number summary because the 5-number summary information is all in here. Here's 4 of them right here on the end, plus the median. Plus we also get the mean, the standard deviation, lots of information. So, so we can look at those. But from this, we can create a thing called a box plot, right? Some people used to call these a box and whisker plot or box and whisker diagram. You don't really hear that as much anymore, but you will kind of see it. It's kind of a silly name. The whisker is just a line, so I'm not sure if someone maybe saw like the shape of a cat or something where they called these the whiskers. I'm not sure what the point of that was. But anyways, we call them box plots now, and StatCrunch will do them for you as well. If you look under graphs, we've got box plots right there. So you can go through and calculate a box plot, and it'll calculate all the necessary values for you, and you can calculate it. Again, whenever you create something like this, make sure you're labeling it well, and of course, make sure you understand it, right? I see when I'm watching videos for the project at the end of the semester, I watch videos where people are presenting things to me like they remembered to, oh, I made a box plot and I made a histogram and here's some different stuff. And it's very obvious who knows what those things are and who sort of like made a box plot and included it in the video, but they don't really understand at all what a box plot is and they can't really explain it. So make sure you take the time to understand the box plot. It seems really complicated at first and like really weird. It's actually not bad at all. So if you spend a little bit of time with it, you probably be okay. Okay, and then you can know what you're talking about when you're making your video. So it basically is another way of visualizing how the data is spread out, right? So you've got the minimum here, maximum here. This middle part of your box is the median, or the second quartile, and then we make these lines for the other quartiles. So this box represents 50% of the data, right? 25% in here, 25% in here, 25% is here, 25% is here. So that actually can kind of tell you, like when we look at a histogram and we can see how it's skewed, this can give us information about how it's skewed as well. One nice thing about the box plot, it's very compact. So a lot of times what you'll see is numerous box plots put together so that you can see change over time. You could say, and you might say, well, wouldn't a histogram do the same? But imagine you have imagine you have 10 histograms. It's kind of hard to judge 10 histograms at a time. It'd be like too much going on because a histogram takes a lot of room. These box plots, you can put like here, you can put a couple of them together and you can see how they change. If you can look up online, and you can, if you look up box plot, temperature, and then like a place, you're probably going to find where someone has put together a box plot representing each month. So you've got your high, your low, and then your daily temperatures as a box plot, and you can actually see how that temperature is moving over time. So like here, we can see that most of the data is way over here. Look, 25% of the data is right here. 25% is here, 25% is here. That means 75% of the data is right here. And this whole area out here is only 25% of the data. That means that our data is very skewed one direction. Whereas here, it's a little more spread out. It's kind of evenly distributed. You can see that by looking at the box plot. So here you can see, again, putting a few of them together, and you can start making comparisons between Chips Ahoy, Keebler, whatever Hannaford is. I take it that's a type of cookie. And you can start comparing those box plots. It's very, very convenient. Let me see if I can look up real quick. So we do box plot, temperature, images. Yeah, here's a good example. So this is why this is a way you see these done a lot. Like if you want to make comparisons of how your data changes over the year or something like that, this is a great idea. So see how they put a bunch of box plots together? Each one of these represents a month and the temperatures. So what are you noticing? Well, we notice one thing. The median temperature is going up in a way you'd expect. It's high in the summer and it's low in the winter. But also look at a few things. Another thing that I can tell by looking at this graph is, look, the variability is also changing over time. All right, where was this? I don't know. This is somewhere, I don't know, it looks maybe Nordic or something, Svalbard. I won't even try to pronounce that because I'll wreck it. But maybe this is some kind of Nordic area. Look how there's this big fluctuation of temperatures here between the max and the min. But look, in the summertime, it's really close together. The temperature barely changes. The maximum temperature from the minimum is like close together. So what that means is in the summer, there's actually a lot less variability in the temperatures than there is in winter, right? And that's extra information that we didn't see in other visualizations, right? So it can be very helpful to put a few of these box plots together and start making comparisons, because it can tell you how skewed the values are for that particular time period, can tell you what's the variability, all sorts of stuff about our data comes through in these types of graphs, which can be really helpful. Okay, and with that, it looks like we just hit 8:50. Let's see, is there anything else I want to say really quick? That should do it. You should be aware, there are some variations in how you can make box plot. There's a thing called a box plot, and then there's a thing called a modified box plot. Like for this class, I wouldn't worry about it too much. If you understand the basics of how a box plot works, and that you kind of get what I just showed you, that you can put a few of them together, and then you can read it like I just talked to you about, don't sweat like all the different versions. Like, just know how to make a box plot reliably that tells the story of your data. Okay, so we will stop there. And like I said, just as a reminder, so hopefully you're getting Chapter 3 done real soon, because Chapter 4 is done kind of right after that. So I will start talking about Chapter 4 on Wednesday. Please take the survey if you haven't done it yet. Please go right now, go take the survey. I really would like to release that data on Wednesday But at this point, we just don't have enough. We need a few more people taking that survey data. So I'll release that. You can start working on your survey stuff. And then also I will cover correlation and scatter diagrams, which are cool. Again, StatCrunch is going to do all the heavy calculating. Our goal will be to understand what's going on and make sense of it. Okay, so I'll close the Zoom. No, I will close the YouTube stream. And if anyone wants to jump over into Zoom and ask me questions, feel free to do so. Otherwise, thanks everybody. I'll see you.